Hello, I'm Sam Estep. I'm presenting gradual program analysis for null pointers. So first, let's start with some motivation, lay out what is the problem that we're trying to solve. So consider this example C program. We have a function that we've written for reversing a string, and then we have a main function that calls it, right? We're thinking about this in the context of analyzing this for null pointer bugs, right? So the function takes in a possibly null parameter. And the idea is that it should safely just return null if it's given null, otherwise it returns the reverse of the string. Notice that when we call it a couple times, first with something that's non-null, then we pass that to puts to print it, which is fine because puts, prints things that are non-null. And then we pass it to puts again, this time calling reverse with null, which causes the program to crash because puts fails if you pass null. So from a static analysis perspective, we would like to get some sort of static warning if we, for instance, omit this check that the parameter to reverse is null, because then when we pass it to strlen, that could segfault, which is not good. We want to make sure that reverse actually doesn't just crash. But on the other hand, a naive static analysis would say, okay, so reverse can return null or non-null. So then when you pass it to puts, I see that, I see that it could be null, so I should give you a static warning, right? But we really don't want that to happen in the case where we're passing in smiley face, because we know that smiley face is non-null. That would be a false positive. But on the other hand, we don't want our program to just segfault when we call puts with a null parameter, right? So we kind of want our analysis to not give too many false positives, but also not be unsound by not warning us or just causing our program to segfault in cases where we use null pointers incorrectly. So what we're going to do is present a framework that is sound, but kind of adjusts the definition of what it means to be sound by, instead of only giving static warnings, also inserting runtime checks. And we call this gradual analysis. So it's a general framework. You can use it for various different kinds of analyses. The paper lays out the formal framework itself. In this presentation, we'll explore it mostly in the context of null pointer analysis. So let's talk about the framework. Just to lay out the big picture, in static analysis, you take a program represented as a control flow graph, and then you pass it to our static analysis system. So this has two parts. First, a fixed point algorithm that uses a flow function, which essentially describes the abstract semantics of the language, and a join function, which basically tells you how to join together two analysis results from different branches. We iterate on this until we reach a fixed point, and that gives us analysis for the entire program. And then we pass it to the second portion, which gives static warnings. So this has a couple of pieces that basically tell the analysis how to determine where the analysis results are okay and where they are concerning and should give a static warning to the programmer. So we run the whole program through this, and we end up with some output, which is a bunch of static warnings. So just as an example, for null pointers, we might have a couple of abstract values, one of which corresponds to the set of all pointers, the other which corresponds to the set of all pointers except for null. These form a lattice or a semi-lattice that is ordered by set inclusion, right? So we take these concrete values, sets of concrete values, and we turn them into abstract values. So this is just standard program analysis abstract interpretation. And it's pessimistic. So later we'll contrast this with what we'll call optimistic abstraction. We also have annotations. So notice here I've modified the reverse function. We want our analysis to be modular, meaning that we don't want to have to analyze a function multiple times. So we annotate the inputs and outputs of the function so that the analysis can analyze the function in isolation. Similarly, other functions like, for instance, puts would have annotation saying that its parameter has to be non-null, which tells the analysis that when puts is called, if it's being passed something that could possibly be null, then we should get a static warning. So again, in order to analyze this, we construct a control flow graph, and then we calculate the fixed point by following this control flow graph using the abstract semantics of the language, and we find this. So for instance, for the For the reverse function, our stir parameter could be nullable in a couple of places. At the beginning of the function, where before we've checked to make sure that it is non-null. And then for all the rest of it, we determine that both of our local variables that are pointers are actually non-null. So that's just kind of an intro. Similarly, when we're analyzing our main function, we generate this control flow graph and we analyze it. And because the reverse function can return null, both of the results of calling reverse are deemed to be nullable by the analysis. And so when we try to pass them to puts, we actually give 2 static warnings, which is kind of annoying because ideally we would like the analysis to only warn us in places where there's actual bugs, but alas, it is not precise enough. So in this case, it thinks that reverse of smiley face could possibly be nullable. It is not context sensitive. Rather than making it context sensitive though, which is a bit computationally expensive, we are going to adjust our view of what static analysis is. We're going to turn it into gradual analysis. So in the next section, we're going to talk about the top 3 orange things that I highlight here, which is lifting the semi-lattice. So instead of having 2 abstract values, we're actually going to have more. The other aspect of it is that instead of only giving static warnings to the programmer when something isn't right, we will also allow ourselves to modify the program to insert runtime checks. So again, this is the semi-lattice, but we also need to have this additional piece where instead of just giving static warnings, we also insert checks. So again, pessimistic abstraction. If you have something that is of abstract value nullable, we assume pessimistically that it could be null in a place where it might be required to be non-null. So we give a static warning. What we're essentially going to do is instead of taking concrete values and taking sets of them and then lifting up into abstract values, we're going to do that a second time, where we take sets of these original abstract values and we lift them to produce lifted abstract values or gradual abstract values. And this is going to be optimistic. So the idea here is that you see that dynamic represents nullable and non-null. And in a situation where we are required to have something non-null, we will optimistically say, oh, dynamic includes that. So we will not give a static warning, but we recall that we're being optimistic and then we will insert a runtime check. So here's an example. If we instead annotate the return value of reverse with dynamic instead of nullable, then we get this situation when we analyze the main function. So both of the returned values from reverse are actually now dynamic instead of nullable. And remember that dynamic includes non-null as one of its represented abstract values. So that means that is actually okay when we try to pass it to puts, because we're optimistically assuming that it actually is non-null, even though in practice this might turn out not to be the case. So this is nice because it means we don't give a false positive for smiley face, but it's not perfect because it means that we actually don't catch the seg fault for reverse, which is bad. So the way that we get around this is we recall the places in which we were optimistic and we insert runtime checks, right? So any case in which our analysis didn't have to be optimistic, we just continue as before, all is good. But in a case where we were optimistic, we insert these checks before calling puts, for instance, that says, hey, if this actually is null at runtime, gracefully step to an error state. Don't just call puts and then let it seg fault or do whatever it would do that is not safe. So again, that's the big picture. We extend our set of abstract values by taking subsets of them essentially, and then optimistically using those subsets to represent multiple different possible abstract values. And then we insert runtime checks in the cases where we're being optimistic in order to retain soundness. So we're going to briefly talk about the mechanism for lifting semi-lattices. I'm not going to go into a ton of detail in this because this is a fairly short talk, but all the details are in the paper. So essentially, what do we want? So if you consider this larger semi-lattice, so the one we had before was 2 elements, this is 5. We could take any number of subsets of this, right? So which subsets do we take? Previously, we just took the 2 singleton sets and the set of all of them, but it turns out we can't just do that in the arbitrary case. The paper lays out a bunch of different properties that we need from our lifting, which we'll go into in some detail. So I think these are slightly out of order, but that is okay. So firstly, we need to include all the original values, right? We're extending our semi-lattice. So we have to have the originals plus some more. We need an abstraction function, which basically just means for technical reasons, we have to be able to go from elements that we do choose, like subsets that we do choose, and arbitrary subsets. So any arbitrary subset, basically we should be able to pick a minimal lifted element that includes that, but it might possibly be larger. And this actually tells us that we have to have one that includes the entire original set of abstract values. We have to provide idempotence. Basically, the idea of this, again, is that we are lifting the set of abstract values into a new semi-lattice. We need to provide a join operation on that new semi-lattice. And so it turns out that, for instance, you can't choose a set like this, because as we define our lifted join operation, this actually turns out to be not idempotent. So we can't choose the subset containing just the abstract values semi-prime and prime power. And this is laid out again in the paper if you want to see why that is. It has to be associative. So for instance, if we include these three singletons and then this set of all three, and then we don't include these two element sets, the lifted join turns out to be not associative, which also doesn't work. We also have to lift it in such a way that retains finite height. So the prior two, we're saying, okay, we have to include certain sets of elements so that it is associative or idempotent. It turns out that we also just can't just include all of them, because then the height might not be finite. So we have to have something that's kind of in between. And so it turns out what we do is this. So we basically say, okay, we're going to include all the singletons. We include one that corresponds to all of them. And then for each individual element from the original semi-lattice, we include an element that corresponds to it and everything above it. So that we write that as if the original element is x, like square free, then it and everything above it would be square free question mark, right? So we can also have, like, for instance, prime question mark. So this gives us kind of a easy formula for if we start out with semi-lattice, what are the elements we get when lifting it? So as mentioned before, we get a new semi-lattice if we lift the join operation using the formula from earlier. And cool. So now we can basically just plug this into our fixed point algorithm. We also have to lift the flow function, but that's fairly mechanical using the techniques that we borrow from the work that we cite. And yeah, that's how you lift an arbitrary semi-lattice. So we're going to briefly discuss our empirical evaluation and then conclude. So basically, we wrote a prototype using Facebook Infer, written in OCaml, so it can analyze these languages. We, in our preliminary evaluation, only analyze Java programs. So in particular, we compared against null-away on a set of repositories where null-away gave no warnings. Null-away is a tool by Uber. We also compared against some checkers built into Infer, such as eradicate and null-safe, and then our own prototype. So as you can see, our prototype obviously didn't do as well as null-away. It gave some false positives on these repositories, but it did give fewer false positives than eradicate and null-safe. Obviously, this isn't the full story. This is only false positives. What about true positives? We did not analyze that in our preliminary investigation. Another thing that we looked at was, given that our analysis is sound, you can actually use it in a particular way, such that instead of just giving warnings at places where you think there might be null errors, you can run it in such a way that you say, okay, assuming that we checked every possible dereference, which of those are unnecessary? And it turns out that actually our tool can eliminate about 67% of possible null dereference sites in the repositories that we analyzed. Again, this doesn't translate directly to performance, but it is interesting that our tool can serve both as a practical tool to eliminate false positives and as a sound tool to find unnecessary runtime checks. Yeah, so in conclusion, this is what we covered. There's more in the paper, specifically more examples, formalism, linked to a prototype that's a Docker image. Evaluation is more detailed, and proofs. And here's some future work that would be interesting to explore. Thank you so much for your attention.